welcome to this problem walkthrough. Today, we'll be discussing problem number 1022, sum of root to leaf binary numbers. This problem is a fascinating exercise in binary tree traversal, where we compute the sum of binary numbers represented by root to leaf paths. Let's dive in and explore the approaches to solve this. In this problem, we are working with a binary tree where each node holds either a 0 or a 1. Every path from the root to a leaf node in this tree forms a binary number. For example, if we follow a path like 0-1-1-0-1, it represents the binary number 01101, which is equivalent to 13 in decimal. The task is to calculate the sum of all these binary numbers formed by root to leaf paths. Since the sum can become very large, we need to return the result modulo 10⁻9 plus 7. A leaf node, in this context, is simply a node that does not have any children. The input to our function will be the binary tree itself, provided through its root node, and the output is a single integer representing the calculated sum. Let's look at an example to understand this problem better. Consider this binary tree with the root node 1. The left child of the root is 0, and the right child is 1. Each of these children further has two children of their own. The binary numbers formed by the root to leaf paths in this tree are 100, which is 4 in decimal, 101, which is 5, 110, which is 6, and 111, which is 7. Adding these values gives us a total of 22. Therefore, the output for this input tree is 22. Now, let's look at a simpler example. Here, the tree consists of just a single node with the value 0. Since there is only one root to leaf path, which is just the value of the root itself, the binary number represented is 0. The sum of all root to leaf paths in this case is simply 0, which is also our output. In another example, we have a tree where the root node is 1 and it has a single left child, also with the value 1. For this second example, there is again only one root to leaf path, which is 1-1. This path forms the binary number 11, which is equal to 3 in decimal. As there are no other paths, the sum of all root to leaf binary numbers is just 3. Hence, the output for this example is 3. With these examples, we see how to compute the sum for both simple and slightly more complex trees. Next, we'll consider some constraints and edge cases to keep in mind when solving this problem. The problem comes with a few constraints and edge cases that we need to handle. First, the number of nodes in the tree can range from 1 to 10⁻4, so our solution needs to be efficient. Also, each node is guaranteed to have a value of either 0 or 1, and the tree itself is always non-empty. For edge cases, if the tree has only a single node, the sum will simply be the value of that node. If all nodes in the tree have the value 0, the sum will also be 0 regardless of the tree's structure. For highly unbalanced trees, where the tree resembles a linked list, we must still compute the binary number correctly. Finally, for large trees, we need to ensure our implementation handles the modulo operation efficiently to prevent overflow and return accurate results. To solve the problem of summing root to leaf binary numbers, one approach we can consider is a brute force method using depth-first search, or DFS. The idea here is to systematically explore all root to leaf paths in the binary tree. At each step, we maintain the binary number as a string, appending the value at each node as we traverse. When we reach a leaf node, the binary string is converted to an integer using Python's built-in int function with base 2, and this integer is added to a running total. While this approach is straightforward, it comes with some computational costs. The time complexity is n*h, where n is the number of nodes in the tree and h is the height, due to the overhead of string concatenation at each level. Additionally, the space complexity is h, which accounts for the recursion stack depth. This method, while easy to grasp, can become inefficient for larger trees due to repeated string operations and memory overhead. Now, one limitation of the brute force approach is the memory overhead caused by creating and converting strings repeatedly, especially in large trees. To address this, we can optimize the solution by modifying our DFS traversal to work with integer accumulation instead of building strings. The key insight here is that binary numbers can be computed directly by treating them as integers. At each step, we calculate the binary value by multiplying the current value by 2 and adding the node's value. This mimics the behavior of binary concatenation but avoids the need for strings. In this optimized approach, we pass the accumulated integer value during recursion. When a leaf node is reached, this accumulated value is added to the total sum. This method improves both time and space efficiency. The time complexity is reduced to O(n), as each node is visited only once, and the space complexity remains O(h) for the recursion stack. This approach is not only more efficient but also well suited for handling larger trees. One of the key observations about the optimized DFS approach is that multiplying by 2 and adding the node's value is equivalent to a left shift operation in binary arithmetic. This makes the computation extremely efficient, as it avoids unnecessary string manipulation entirely. By directly accumulating the binary value, we streamline the process and significantly reduce memory usage. This approach also eliminates the repeated conversions that were a bottleneck in the brute force method. However, there are trade-offs to consider. While this method is more memory efficient and avoids overhead, it may be slightly more challenging to implement than the brute force approach, as it requires a deeper understanding of binary arithmetic. An alternative to DFS is breadth-first search, or BFS, which processes the tree level by level. In this strategy, we maintain a queue of nodes along with their accumulated binary values. This iterative method avoids recursion but introduces its own trade-offs in terms of space usage, as the queue can grow large for wide trees. When considering the BFS approach, we observe that its complexity is similar to DFS in terms of time, requiring O(n) to process all nodes. However, the space complexity depends on the maximum width of the tree, represented as O(w), where W is the size of the queue. This makes BFS particularly advantageous for very deep trees, as it avoids the risk of recursion stack overflow. On the other hand, the iterative nature of BFS can make implementation slightly more complex compared to DFS. Additionally, the memory usage in BFS can be higher in cases where the tree is very wide. In contrast, DFS with integer accumulation typically has a smaller memory footprint, as the recursion stack is often less demanding than the queue used in BFS. Each approach has its merits, but the choice depends on the specific problem constraints and the structure of the binary tree. The chosen strategy for this problem is the optimized DFS approach with integer accumulation. This method strikes a balance between simplicity and efficiency, making it ideal for solving the task. By directly computing the binary value during traversal, we eliminate the overhead of string operations and conversions that make the brute force method less scalable. Compared to BFS, this approach uses less auxiliary space in most cases since the recursion stack is typically smaller than the queue required for BFS and wide trees. The DFS strategy also ensures a time complexity of O(n), which is optimal, and a space complexity of O(h), which is minimal for a depth-first traversal. While it may require a slightly deeper understanding of binary arithmetic, the benefits of efficiency, memory optimization, and straightforward implementation make it the most practical and robust solution for this problem. To solve this problem, we need to calculate the sum of all root-to-leaf binary numbers in a binary tree. Each node in the tree contains a binary digit, either 0 or 1. As we traverse from the root to a leaf, the sequence of digits along the path forms a binary number. For example, in a tree with the paths 1-0-1 and 1-1-0, the binary numbers formed are 101 and 110. Converting these to decimal, we get 5 and 6, and their sum is 11. A simple way to approach this is to use depth-first search, or DFS. The brute force method involves exploring all root-to-leaf paths. Along each path, we construct the binary number as a string, convert it to a decimal integer, and accumulate the total sum. While straightforward, this method does come with inefficiencies. Let's break it down step by step. First, we handle the base case where the tree is empty. If the root node is null, we simply return 0 as the sum. Next, we define a helper function, DFS, that takes two arguments, the current node and the binary number formed along the path so far, represented as a string. For leaf nodes, where both left and right children are null, we append the current node's value to the path string. Then, we convert the binary string to a decimal value using Python's int function with base 2 and add this value to our result. For internal nodes, we continue appending the current node's value to the path string and recursively call the DFS function on the left and right children, if they exist. Finally, we combine the sums returned from the left and right subtrees and return the total. This process ensures that every root-to-leaf path contributes to the final result. Using DFS guarantees that all root-to-leaf paths are visited in an orderly fashion, and each path is processed independently. However, building binary numbers as strings and converting them to integers introduces overhead. This makes the algorithm less efficient compared to techniques that avoid string manipulation. In terms of space complexity, the recursion stack depends on the height of the tree. For a balanced binary tree, the height is proportional to the logarithm of the number of nodes, resulting in O log n space complexity. However, in the worst case of a skewed tree, where all nodes are either left or right children, the height becomes equal to the number of nodes, leading to O n space. We also consider edge cases such as an empty tree, which returns 0, or a single node tree, which simply returns the node's value. For trees with large depths, it's important to ensure that the recursion depth does not exceed system limits. The problem involves a binary tree where each node stores a binary digit, either 0 or 1, and each node can have up to 2 children. To represent the binary numbers formed along root-to-leaf paths, we use strings in this brute force approach. Strings are easy to append to, as we can simply concatenate the current node's value to the path string. However, for deeper trees with longer paths, this can become less efficient compared to using direct bitwise operations. Looking at a simple example, consider a binary tree with the structure: the root node is 1, which has 2 children, 0 on the left and 1 on the right. The left child, 0, has a further left child, 1. The right child, 1, has 2 children, 0 on the left and 1 on the right. The paths from root to leaf are 1-0-1, 1-1-0, and 1-1-1. These correspond to binary numbers 101, 110, and 111, which convert to 5, 6, and 7 in decimal. Adding up these values, we get a total sum of 5 plus 6 plus 7, which equals 18. The time complexity of the brute force approach is O, n, where n is the number of nodes in the tree. This is because each node is visited exactly once during the DFS traversal. The space complexity is determined by the height of the tree, which corresponds to the maximum depth of the recursion stack. For a balanced tree, this is O log n, while for a skewed tree, it is O n. To optimize this approach, we can use bit manipulation instead of strings. By representing the binary number as an integer, we can append digits using bitwise operations. For example, shifting the current number left by 1 bit and performing a bitwise or with the current node's value achieves the same result as string concatenation but with much less overhead. Another optimization is to use an iterative DFS with an explicit stack instead of recursion, which avoids potential issues with recursion depth limits in very deep trees. This solution solves the problem of summing binary numbers formed from root-to-leaf paths in a binary tree. The approach uses depth-first search (DFS) traversal to explore all paths and compute their binary values efficiently. The sum root-to-leaf function is the main entry point. It calls a helper function DFS with the root node and an initial value of 0 to represent the current binary number being formed. The DFS function is recursive. For each node, the function first checks if the node is none. If it is, it returns 0, as there is no contribution to the sum from a non-existent node. Next, the function calculates the updated binary value for the current path by shifting the current value 1 bit to the left, using current 1, and adding the node's value, using bitwise OR. This efficiently constructs the binary number as we traverse down the tree. If the current node is a leaf node, it has no left or right children, the function simply returns the current value, as this represents the complete binary number for this path. If the node is not a leaf, the function recursively computes the sum for its left and right children, passing the updated current value to each call. The results from the left and right subtrees are added together and returned. Finally, the sum root-to-leaf function returns the total sum of all root-to-leaf binary numbers by invoking DFS on the root node. This solution is efficient, with a time complexity of O, n, where n is the number of nodes in the tree. This is because each node is visited exactly once. The space complexity is O, h, where h is the height of the tree, due to the recursive call stack. Here, we begin by defining the structure of a binary tree node using the treeNode class. Each node has an integer value, along with references to its left and right children. This provides the foundation for representing our binary tree. Next, we define the main function, SumRootToLeaf, which takes the root of the binary tree as input. This function calls a helper method, DFS, passing the root node and an initial value of 0. The DFS method is where the depth-first traversal logic is implemented. It starts by checking if the current node is null. If it is, we simply return 0, as there's no value to contribute. This handles the base case for recursion when we reach the end of a branch. Now, within the DFS method, we update the current value by shifting it one bit to the left and adding the value of the current node. This effectively builds the binary number as we traverse down the tree. If the current node is a leaf node, meaning both its left and right children are null, we return the accumulated current value, as this represents a complete binary number from root to leaf. Otherwise, we recursively call DFS for the left and right subtrees, passing the updated current value to each. The results from the left and right subtrees are added together and returned, ensuring that all root to leaf paths are considered in the final sum. Let's begin by looking at a simple binary tree example. The tree has a root node with the value 1, and it splits into two children. The left child has a value of 0, and the right child has a value of 1. The goal is to find the sum of the binary numbers formed by the paths from the root to each leaf. Starting at the root node, the current value begins at 0. We update it by shifting the current value left by 1 bit and adding the root node's value, which results in 0, 1, 1 equals 1. Since the root has both left and right children, we proceed recursively into both subtrees. First, moving to the left child with value 0, we again update the current value as 1, 1, 0 equals 2. This node is a leaf, so we return 2 as the binary sum for this path. Then, we move to the right child with value 1. The current value updates to 1, 1, 1 equals 3, and this is also a leaf, so we return 3 as the result for this path. At this point, we've calculated the binary sums for both paths in the tree. The left path contributes 2, and the right path contributes 3. To determine the total sum, we add these values together, which gives us 2 plus 3 equals 5. For this example, the final output is 5. Now, to get a deeper understanding of the approach, let's examine a larger binary tree. In this example, the root node again has a value of 1, with left and right children. The left child leads to a subtree with a single additional leaf, while the right child leads to a subtree with 2 leaves. The binary numbers formed from root to leaf are 101, 100, and 111, which correspond to the decimal values 5, 4, and 7, respectively. Starting at the root, the current value begins at 0 and is updated to 0, 1, 1 equals 1. From here, we recurse into both the left and right subtrees. First, we explore the left subtree. Moving to the left child with value 0, the current value updates to 1, 1, 0 equals 2. Continuing to its left child, which has a value of 1, we update the current value again as 2, 1, 1 equals 5. This node is a leaf, so we return 5 as the result for this path. Next, we backtrack to the root to explore the right subtree. Moving to the right child with value 1, the current value updates to 1, 1, 1 equals 3. From here, we recurse into its left and right children. First, we move to the left child with value 0, updating the current value to 3, 1, 0 equals 6. This node is a leaf, so we return 6 as the result. Then, we move to the right child with value 1. For the right child of the right subtree, the current value updates to 3, 1, 1 equals 7. Since this is a leaf node, we return 7 as the result for this path. At this point, we have the results for all the root to leaf paths, 5 from the left subtree, and 6 and 7 from the right subtree. Adding these together gives us a total sum of 5 plus 6 plus 7 equals 18. Therefore, the final output for this example is 18. Now, let's consider an edge case where the tree consists of only a single node. In this scenario, the binary number formed is simply the value of the root itself. In the single node tree example, the root has a value of 1, and since there are no other nodes, the current value starts at 0 and updates to 0, 1, 1 equals 1. This node is also a leaf, so we directly return the current value as the result. The binary number formed is 1, which corresponds to the decimal value 1. Thus, the final output for this edge case is 1. The time complexity of our solution is O(n), where n represents the number of nodes in the binary tree. This is because the DFS function is called exactly once for each node. During each function call, only a constant amount of work is performed. Specifically, the calculation current equals current1 node.val involves a left bitwise shift and an OR operation, both of which are O(1). Additionally, checking if a node is a leaf, using the condition not node.left and not node.right, is also O(1). The recursion then proceeds to explore both the left and right subtrees, ensuring that all child nodes are visited exactly once. Since each node is processed only once, and each visit involves constant work, the total time complexity is directly proportional to the number of nodes, resulting in O(n). Now, let's analyze the space complexity. The space used by this solution is dominated by the recursion stack during the depth-first traversal. The maximum size of the recursion stack is determined by the height of the binary tree. In the best case, when the tree is perfectly balanced, the height of the tree is O log n, which means the recursion stack will require O log n space. In contrast, in the worst-case scenario of a completely skewed tree, where all nodes are aligned to one side, the height becomes O(n), resulting in a recursion stack space of O(n). It's important to note that aside from the recursion stack, no additional data structures are used in this solution. Therefore, the overall space complexity is O(h), where h represents the height of the tree. This simplifies to O log n for a balanced tree and O(n) for a skewed tree. Finally, let's compare this optimized approach to a naive or brute force solution. A brute force method might involve generating all possible root-to-leaf paths, then converting each path into its decimal value and summing the results. This approach would require extra space to store these paths and additional time to perform the path-to-integer conversions. Specifically, the time complexity of the naive approach would be O(n*(m), where m is the average length of a path, equivalent to the tree height. For a balanced tree, this simplifies to O(n log n), and for a skewed tree, it becomes O(n²). The space complexity of the brute force method would also increase due to the need to store all paths, reaching O(n) in the worst case. In contrast, our optimized solution directly calculates the sum during the traversal itself, avoiding the storage of paths and redundant computations. This ensures a linear time complexity of O(n) and a space complexity of O(h), where h is the tree height. For balanced trees, this means O log n space, and for skewed trees, O(n) space. Overall, the optimized approach is significantly more efficient in both time and space usage. When solving this problem, there are several common mistakes to avoid. First, using string concatenation instead of bitwise operations is a frequent error. While it might seem straightforward to build the binary number as a string, this approach is both slower and more memory-intensive, especially for deeper trees. Bitwise operations, on the other hand, are more efficient and directly suited for this type of problem. Another common pitfall is incorrect base conversion. It's crucial to remember that binary numbers are positional, meaning each digit's value depends on its position from the right. For example, 101 represents 1 times 2 to the power of 2, plus 0 times 2 to the power of 1, plus 1 times 2 to the power of 0. Ignoring these positional weights and summing node values directly as integers leads to incorrect results. Finally, overlooking edge cases like single-node trees can cause issues. A tree with only one node is entirely valid, and failing to handle this scenario properly might result in runtime errors or wrong outputs. Always account for these nuances in your implementation. Now, let's discuss two more common mistakes. Mismanaging leaf nodes is another frequent error. Leaf nodes, by definition, are nodes that have no children. If you mistakenly include non-leaf nodes in the final sum, you'll end up overcounting, which leads to incorrect results. It's essential to carefully identify and process only the leaf nodes in your solution. Another inefficiency arises from recalculating the binary number for each path from scratch. Instead, you should pass down the accumulated binary value through the recursion stack. This approach avoids redundant computations and ensures the solution runs in O(n) time complexity. If you ignore this optimization, the time complexity can balloon to O(n²) for deeper trees, significantly slowing down your solution. Efficient tree traversal is key to solving this problem correctly and within optimal time limits. Understanding the broader context of this problem can help you stand out in interviews. This challenge is part of a family of root-to-leaf path problems in binary trees, which are commonly used to assess your ability to traverse trees efficiently and manage state during recursion. Interviewers often look for solutions that handle edge cases well and demonstrate a deep understanding of recursion. The optimal approach for this problem involves using depth-first search, or DFS, with bitwise operations to propagate the accumulated binary value down the tree. This method ensures a time complexity of O, n, where n is the number of nodes, and a space complexity of O, h, where h is the height of the tree. Interviewers may also ask follow-up questions, such as how to adapt your solution for a general base k-number system instead of binary, or how to solve the problem iteratively without recursion. Additionally, it's helpful to explore related problems, like path sum and binary tree paths, which share similar traversal techniques and problem-solving patterns. Finally, let's consider some alternative approaches. One option is the string conversion approach, where you build the binary number as a string during tree traversal and convert it to an integer at the leaf. While this is simpler to implement, it's less efficient due to the overhead of string operations. The time complexity remains O, n, but the constant factors are worse compared to bitwise operations. Another approach is using breadth-first search, or BFS. Here, you maintain a queue to perform level-order traversal, keeping track of the accumulated binary value for each path. This avoids recursion but increases space complexity to O, n, in the worst case, due to the need for the queue. Lastly, you can use an iterative DFS with a stack. This simulates the recursive DFS by explicitly managing a stack to store the current node in accumulated binary value. While it eliminates recursion and avoids potential stack overflow, it requires careful stack management and is generally less intuitive than recursive DFS. Each of these methods has its trade-offs, and understanding them can help you adapt your solution to different constraints or interview scenarios. Great job reaching the end. In this walkthrough, we explored the problem sum of root-to-leaf binary numbers and discussed how to use DFS to solve it effectively. Remember, mastering tree traversal is essential for similar problems. Thanks for watching, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!